So Larissa's not here. She's in Chicago. I told her we'd give a shout out to her. So Sarah, you want to say hi to Riz?
Hi, Riz. I hope you're having fun in Chicago.
Riz, I want a slice of deep dish Chicago pizza. That's what I want. So if you could bring that back, that'd be great. Okay, that's what we want. You're going to see that today what we do is going to be very, very similar to what you've done before. Sometimes there's just a difference in notation, okay? What we're going to do is we are going to start by diagramming the linearization of the function and the formula. And so our goal today is to say I can find the linearization of a function, and we also want to be able to say I can find the differential of a function. Okay, so we want to be able to do those couple things, or I can math real good. Okay, so okay, so what have I drawn so far? Tangent line. We are going to call these points a few different things. We're going to call this A. What would that make this spot here? F of A. A for the day, what is the slope of the line? How do you find slope? You take the derivative, and then you evaluate it at the x value, which would be A. Now, would you agree that that line is most definitely different than the function? Okay. But would you also agree that if I looked at simply this portion, if I zoomed in right here, would you agree that there is not much of a difference between the function and the line? As a matter of fact, can you see where the term linear approximation now comes from? The linear approximation is the linear representation of the function. It is very similar to the function. Is this line an underestimate of the function or an overestimate of the function? Underestimate. It's always below the function, but it's very close. So if we can write an equation for this line, we would have a very close linear approximation for the function. So what I'm going to do is I'm going to put in my key values, and I'm going to now use this notation. Forget about y equals mx plus b. We're going to use this. Y minus y1. What's my y1 value? F of a. What's m? Yep, f prime of a times x minus a. So, the linear approximation, this is nothing different, you guys, than a tangent line at a given point on the function. It's just a different way of writing it. If I add the f of a over, I get f of a plus f prime of a times x minus a. It's like, what's the point? Well, in the theory of calculus, as calculus develops, and as we use calculus 2 later on, some of this notation, as we then go from linear approximation to differentials, is going to be important. There's a whole study of calculus called differential equations. So this lays just a little bit of groundwork. So these are going to be some important things that you might see in the future. But let's just see why this is useful. Okay? Why would linearization of a function be useful? It is sometimes difficult to evaluate certain functions. For example, y equals tangent of 3 pi minus 4. That might be a difficult number to come up with, right? So sometimes you plug a number into a function, you're like, well, how do I come up with it? You know, that's kind of a tough number to get. Remember, you guys, when this was being developed, did they have calculators? So let's suppose that they wanted to find this. Square root of 4 is easy, right? But the square root of 4.01, that's difficult. It's close to 4, right? It's close. And so the idea of a linear approximation could be a quick way of achieving answers that would otherwise be very difficult. If I told you right now to find a good approximation of the square root of 4.01, I would guess that most of you wouldn't come up with something a whole lot different than 2. But for people like Isaac Newton and others, they would say, well, let's find a quick method for coming up with a really good approximation for what that is. Do you ever wonder how your calculator actually does that? Your calculator uses this awesome formula, and I'll show you guys in about a month, but we want to come up with that. So it is sometimes difficult to evaluate certain functions. Easy to evaluate linear functions. So linear approximation says this. You can take any function that you can find the derivative of, and instead of writing it as a complicated function, like a square root or a tangent or something like that, you can write it in the form of a line. If we can write it in the form of a line, values are easy to come up with. So let's try the basic algebra stuff that we want to do. It says find the linearization of the following functions. Y equals 4x squared minus 1 at x equals 1. Well, we're just going to do the same stuff that we've done before. We need a, and we need f of a, or my point on my line, and I need my slope. Slope is f prime of a. First things first, what is a? 1. What is f of a? 3. Everybody see how Larry got that? Plugged in the original. In order to find f prime of a, I first need to find the derivative. And y prime is equal to 8x. So therefore, m is equal to 8. I always do use the y equals mx plus b, but just for the sake of something we're going to move to later on as well, I'm going to write it like this. Y minus y1 equals m times x minus x1. That's how Elizabeth does it all the time. So y minus 3 equals 8 times x minus 1. Or y minus 3 equals 8x minus 8. Add 3, y equals 8x minus 5. Yep. Now, have you done this skill before? Yes, we've found this is just an equation for a line tangent, is it not? So here's what I want you guys to understand though. okay? This line, y equals 8x minus 5, not only is it the tangent line, but now we're going to define it, just like our picture shows, as the linear approximation of that function. It's very, very similar to the function. And so the idea is, was it easy to plug in 1 there? Yeah, but what if I wanted to know the function's value for 1.01? That would be more difficult, wouldn't it? Would you rather plug in 1.01 to 4x squared minus 1, or would you rather plug it into 8x minus 5? 8x minus 5. And you would come up with a very close approximate value. Does everybody understand that idea? Now, I plugged in, if I plug in 1.01, that's not that far away, is it? But what if I chose to plug in 8? It wouldn't be a very good approximation anymore, would it? So it's if you want to find values, they're very close. Okay, let's do the next one. Y equals negative sine of 2x at x equals pi over 2. We want to find the linearization of the function at that given spot. So I need a coordinate and I need slope. First I have pi over 2. I've started throwing more trig because we need more exposure to it. So anybody know what the sine of 2 times pi over 2? Sine of pi is 0. That was great. I like that. I like that stuff. That's good stuff. Yeah. Oh, for the amplitude? I'll give her a break on that. Yep. Oh. Solveig couldn't find an x-intercept of a linear function yesterday. So. That's what happens when you do calculus. You forget all the basic math. So, okay. I have to find the derivative. If I want to find the derivative of negative sine of 2x, what do I have to use? Chain rule, right? Negative sine of u. And I have 2x. Okay? So derivative of negative sine of u is negative cosine of u. And I get 2. So the derivative, y prime, is negative 2 cosine of 2x. Well, if you want to find what the slope is, what value do you plug in? Pi over 2. Cosine of pi is negative 1. Cosine of pi is negative 1 times negative 2 is positive 2. So we write out our formula. Y minus y1 equals m times x minus x1. And we get y minus what? 0. So you just have y is equal to m, which is 2, times x minus pi over 2. Or y is equal to 2x minus pi. Now, again, I want you guys to understand you plugged in 0.1. We plugged in pi over 2, okay? Say we want to plug in a value very close to that. It would be easier to plug into the linear function as opposed to the sine of 2x. Coming up with sine values, you have a calculator. Again, remember back in the day, they did not have that calculator. They maybe had some tables and stuff like that that they could use. But this linear approximation is a great way of moving forward. Okay? All right. Find the linearization now of square root of 4 minus x and use it to actually approximate the value of 3.99 and 4.1. So now we're actually going to put it to work. Okay? We're going to actually put it to work. Okay? So, let's look and see what value we have here, okay? What we want to do is we want to find the linearization of this function, and we want to use it to approximate these values. So, you tell me, okay, this is where you got to think a little bit. This is 4 minus x, okay? And this is 3.99 and 4.1. These are very close to a value of what? They're both very close to 4. Shh. So what would you plug in for x to give you 4? 0. So we're finding the linear approximation of f of x equals the square root of 4 minus x at x equals 0. And the reason why we want to do it that way is we want to approximate these values. And plugging in 0 for x gets us really close, right? So again, we got this drawing. We want to get really close to that spot we want to evaluate. So let's find the linearization at 0. All right. So the first thing I need to do is find a point on my line, right? The point on my line is going to be 0, 2. Now I need to find the slope. In order to find the slope, I need to take the derivative. Very good. So we have to use the chain rule. I have u to the 1/2 and 4 minus x. So I got 1 over 2 roots of u and negative 1. So f prime of x is equal to negative 1 over 2 roots of 4 minus x. So to find the slope, what value do I plug in? 0. And if we plug in 0, negative 1/4. So, if we plug in 0 for y, we just get, or y1, we just get y equals, I'm sorry, y minus 2 equals our m negative 1/4 times x minus 0. Or y minus 2 equals negative 1/4 times x. Y equals negative 1 over 4 times x plus 2. Now, this is the linearization. Now what we need to do is we need to use it. Because it says use it to approximate these. Now a lot of times people see it and they're like, well, I want to plug in 3.99. No. Very good. What we want to plug in is we're going to use negative 0.1, or I'm sorry, negative 0.01. And positive . Oh, yes. There we go. Yep. So, what we chose is x equals 0 is the spot for our linearization, right? So, the deal is that we want to come up with 3.99. So we said 4 minus x equals 3.99. We solved for that. We subtracted 4. We got negative x is equal to negative 0.01 divided by negative x is equal to 0.01. And then we did the same thing. we did the same thing for 4.1 then. So if we want to actually approximate these values, again, we are going to use 0.01. If we plug that in, we get, let's try to do this by hand, no calculator. Y equals, negative 1/4 is negative 0.25 times 0.01 plus 2. If I take negative 0.25 times 0.01, that's going to move the decimal point 2 places. So I have negative 0.0025 plus 2. Right? That is approximately the square root of 3.99. Let's check. Take your calculator. Oh, hey, that was pretty close, wasn't it? And so you can see how this would be a useful estimation, can't you? Okay, let's do the next one. Okay, negative 0.25 times negative 0.1. Now, you guys, which one's actually closer to our linearization? The square root of 3.99 or the square root of 4.1? Square root of 3.99, that's only a change of 0.01, whereas the 4.1 is a change of 0.1. So we're guessing that this is going to be a little bit further off. If I check on my calculator, and I go the square root of 4.1, 2.0248, still pretty good. So can you see the value in it? Okay, we have other stuff to cover, but the fact is we're not going to get through it anyway, so let's just give you the front half of your assignment, and you can start working on these skills. We'll finish this up on Monday. Did I say draw it? Oh. Yeah, we should draw it. It goes real fast. What shape is it? Yeah, and since it's a negative x, it's reflected over the y-axis, so it goes 1, 2, 3, 4. It starts here, and it goes this way. Now we were finding the linearization at what value? X equals x equals 0. So as you look at this drawing, everybody, okay, the linearization is at an overestimation or an underestimation? We had an overestimation. You can see that we focused in on x values of negative 0.1 and positive 0.01. So we focused on values really close to that spot right there. We kind of looked right in on this spot right there, and you can see that the red line is going to be above that that blue function. Kind of get the concept of what's happening? That's all. That's it. Just need to understand that that's, in fact, we were at an overestimation. Okay, I'll pause this. I'll give you your assignment. Okay, so today we did linearization. On Monday we do differentials, and that will wrap up. I will then let you know exactly what you'll have for your in-class test or take-home test, deciding how we do it. But you should make sure that your related rates are good to go. I promise that I will have your answer key for the related rates done by Monday. And if I do not, I will bring you treats in addition to my birthday treats. So, who's going to hold me to this promise? Okay. Megan Stark, Colin Yonke, and Brooke Hansen will hold me accountable if I do not have the answer key for related rates done on Monday. I owe you all treats before the end of the week next week. My birthday is on December 22nd, and so if you are already shopping for the gift, which you should be, I take just general cash, credit, gift cards. I'm really not picky, so it's all good. So I will bring you guys treats for my birthday though. So I have to bring them for each class though. How about my 7th hour? Should I bring it for my 7th hour? 7th hour doesn't really bring treats, so. Bye, Riz.